Today's discussion is for critical speed of rotor with consideration of moment of inertia of the disk. In the previous videos, we have seen how to calculate the critical speed of rotor without consideration of moment of inertia. That means mass of disk is considered as a point mass. However, in this video, we'll see the critical speed calculation based on consideration of mass moment of inertia of disk. But moment you select the mass moment of inertia of disk, we can have now rotating and non-rotating type of critical speeds. So let's begin the discussion and understand the calculation part of critical speed. The main division of discussion has been three categories, that is theory part, procedures and calculation. So theory part, the general method for critical speed of rotor with the moment of inertia of disk is considered. The main feature is rotor is considered flexible and so the bearing is considered rigidly supported, and so displacement of rotor at bearing is not considered. This method provides the first and higher critical speed with accuracy. Mass moment of inertia of disk is considered and also calculating for non-rotating and rotating critical speed. So these are the main points that are considered for calculation of critical speed. The shear force, these are the shear force, bending moment, slope and deflection equation. The shear force at station n is Vn is equal to Vn minus 1 plus Mn minus 1 into omega square Yn minus 1. So there is no much change in the shear force equation. However, there is a change in bending moment at station n on right hand side. So each station has now two bending moment, one on left hand side which is denoted as L, and another is right hand side, it is denoted as R. So at station M it is M n R is equal to M n minus 1 plus Vn into Ln plus delta Mn minus 1. So this delta Mn is bending moment of the disk, bending moment due to consideration of mass moment of inertia of disk. Slope at station n is theta n is equal to theta n minus 1 plus beta into m n minus 1 r upon 2 plus m n l upon 2 bracket close. Then deflection at station n is yn is equal to yn minus 1 plus theta n minus 1 into ln plus beta n into m n minus 1 r upon 3 plus m n l upon 6 bracket close into ln, where delta m n minus 1 is equal to bending moment due to disk, and which is equal to I bracket start ip minus id bracket close into omega square into theta n minus 1. Ip is a mass moment of inertia of disk about axis of symmetry, which is equal to md into capital D square upon 8 kg meter square, and id is the mass moment of inertia of disk about cg and perpendicular to the axis of symmetry, which is equal to md into bracket start capital D square by 16 plus h square by 12 bracket close kg meter square. Md is the mass of disk in kg, capital D is outer diameter of disk in meter, h is width of disk in meter. For rotating case critical speed, if it is considered rotating case, then delta m n minus 1 is equal to bracket start ip minus id bracket close into omega square into theta n minus 1. For non-rotating case, delta m n minus 1 is equal to minus id into omega square into theta n minus 1. where IP is 0 for non-rotating case. Mode shape and bending moment at last station for simply supported rotor. The starting station is from the bearing, and so following assumption for part 1. Shear force at station 0, V0 is 1. Bending moment at station 0 on left hand side, so it is written as M0L is 0. Slope at station 0, theta 0 is 0. Deflection at station 0, Y0 is 0. This is for part 1. Similarly for part 2, shear force at station 0, V0 is 0. Bending moment at station 0 on left hand side, it is written as M0L is 0. Slope at station 0, theta 0 is 1. Deflection at station 0, Y0 is 0. So for the mode shape, Yn is equal to Yn part 2 minus Yn part 1 into Y10 part 2 upon Y10 part 1. This is sharp deflection equation for different station. Similarly, bending moment at station 10 on right hand side, M10R is equal to M10R part 2 minus M10R part 1 into Y10 part 2 upon Y10 part 1. Now this is a procedure. We'll see the various steps how critical speed is calculated. This is a special case of simply supported rotor. So simply supported rotor has a bearing at each end. Number of shaft span is 1, which is between the bearings. Mass is allocated at different station and denoted as M0, M1, M2 up to M10. Length of shaft segment is denoted as L1, L2, L10. You can see here. Diameter of shafts is denoted as D1, D2, D3 up to D10. Bending moment is calculated on left hand side and right hand side for each station. So this is for a special case of simply supported rotor with a span 1 and station is 0 to 10. Number of stations, that is now steps for calculating the critical speed. Number of stations are chosen as per the convenience, and more the number of stations and the more the accuracy of critical speed. Typical stations are from 0 to 10 are chosen as reasonable accuracy. Note that station number 0 and 10 are for location of bearing. Mass of shaft segment is equal to density of shaft into cross section area into shaft length between the two stations. Mass is allocated at each station such that the total mass of shaft segment is equal distributed on each side of the station. If additional mass is allocated to a particular station, then that that mass is added in that station. Let's say mass at a station is noted as M0, M1, M2 and M10. Calculate area moment of inertia of each shaft segment, that is I is equal to pi by 64 d to the power 4. Unit will be m to the power 4, where d is diameter of shaft in meter. Calculate flexibility constant for each shaft segment. Veta is equal to L upon EI. Unit will be 1 upon Newton meter, where L is the length of shaft. E is the Young modulus of elasticity, which is in Pascal. Now the part 1 rotor, station number 0 to 10. Calculation has to be done part 1 and part 2, and select the suitable value of angular velocity omega radian per second. Part 1, initial assumption or initial condition, station number 0. Shear force V0 is 1, bending moment at left hand side M0L is 0, slope theta 0 is 0, deflection Y0 is 0. Station 1, shear force V1 is V0 plus M0 omega square Y0, bending moment on right hand side at station 1 M1R is equal to M0 plus V1 L1 plus delta M0. Bending moment due to disk delta M0 is equal to bracket start IP minus ID into omega square into theta 0. Mass moment inertia about the axis of symmetry, IP is equal to md into capital D square by 8 kg meter square, and mass moment of inertia of disk about CG and perpendicular to axis of symmetry, ID is equal to md into bracket start D square upon 16 plus h square by 12 bracket close kg meter square. Slope theta 1 is equal to theta 0 plus beta 1 into bracket start m n m0 r upon 2 plus m1 l upon 2 bracket close. Deflection y1 is equal to y0 plus beta 1 into bracket start m0r upon 3 plus m1 l divided by 6 bracket close into L1 plus theta 0 into L1. So in this way, keep on calculating shear force, bending moment, slope and deflection until station 10. Now part 2, initial condition. Station number 0, shear force V0, 0, bending moment on left hand side M0L. It is not written, it should be M0L, not M0. M0L is 0. Slope theta 0 is 1. Deflection Y0 is 0. Then shear force V1 is V0 plus M0 omega square Y0. Bending moment on right hand side of the station 1 M1R is equal to M0 plus V1 L1 plus delta M0, and bending moment due to disk M0 is equal to IP minus ID into omega square theta 0. Mass moment of inertia about axis of symmetry IP is equal to md into d square by 8, and mass moment of inertia about CG perpendicular to axis of symmetry ID is equal to md into bracket start d square by 16 plus h square by 12 bracket close. Slope theta 1 is equal to theta 0 plus beta 1 into m0r upon 2 plus m1l upon 2 bracket close, and deflection y1 is equal to y0 plus beta 1 into m0r upon 3 plus m1l upon 6 bracket close into L1 plus theta 0 into L1. So in this way, keep on calculating shear force, bending moment, slope and deflection until station number 10. Bending moment at last station 10 on right hand side of span. So bending moment at last station on right hand side, that is M10R is equal to M10R part 2 minus M10R part 1 into Y10 part 2 upon Y10 part 1. So to find the critical speed, find the suitable value of angular velocity omega such that the bending moment at last station, that is station number 10, to become 0, and corresponding value of angular velocity is called the critical speed in radian per second. To convert the critical speed in RPM, just multiply with 60 and divide with 2 pi. Select the next higher value of omega such that the bending moment at the last stage to become 0, and corresponding value of angular velocity is called critical speed in radian per second for higher modes. So in this way, more number of critical speeds are calculated. Now this is mode shape of critical speed. Shaft deflection yn is equal to yn part 2 minus yn part 1 into yn part 2 upon yn part 1. So where n denotes the number station number, so for n0 it denotes station number 0, and 1 is station number 1, so on. So mode shape of shaft is drawn shaft length on x-axis and shaft deflection y-axis for particular critical speed. This will provide some mode shape for that critical speed. Note that the deflection is not the actual deflection of rotor, but it is the mode shape of rotor for particular critical speed. Now the calculation part. Rotor is simply supported in both in bearing load. There is a load at disk at midpoint of 100 kg, and outer diameter and width of disk is 0.25 and 0.1 meter respectively. Density and elasticity of shaft is 7.85 into 3 kg per meter cube and 2.1 into 10 to 11 Pascal respectively. Shaft diameter 0.165 meter, shaft length is 1.8 meter. Calculate the rotating and non-rotating critical speed of first and second mode. So this is the diagram for rotor. Mass moment of inertia, axis of symmetry IP is calculated 0.78. Similarly, mass moment of inertia about CG and perpendicular to symmetry ID is calculated as 0.47 kg meter square. So non-rotating case, it is written as minus 0.47 kg meter square when IP is 0, and when rotating case IP minus ID, it is coming as 0.31 kg meter square. Now for non-rotating case, first critical speed is 4813 rpm, where bending moment at the last station on right hand side it becomes 0. So this is non-rotating case. Now this is a mode shape of first critical speed non-rotating case. This looks like this, where x-axis is shaft length and y-axis the deflection of shaft at various station for non-rotating first critical speed. Now this is a rotating first critical speed 4813, and at corresponding the angular velocity of this critical speed, you will the bending moment at the last station on right hand side it becomes 0. This is a rotating case first critical speed or mode shape. X-axis is a shaft length, y-axis deflection. This is similar. Now the non-rotating case second critical speed is 24,355, where corresponding the angular velocity, the bending moment at last station number on right hand side it becomes 0. So this is a mode shape for non-rotating second critical speed, that is 24,355. X-axis is length of the shaft, y is the deflection of shaft at different station. Now this is rotating case of second critical speed, which is now 25,134 rpm, corresponding the critical speed. The bending moment at the last station is 0. This is a mode shape for rotating second critical speed, that is 25,134, and x-axis is the shaft length, y-axis is the deflection shaft at different station. This is the mode shape of rotating case of second critical speed. So this is summary of non-rotating and rotating case. So first critical speed non-rotating 4813 and rotating 4813. But second critical speed non-rotating to 4355 and rotating by 25134. So what are the observation? The first critical speed for non-rotating and rotating case are same. For the second critical speed for non-rotating and rotating case are different. Rotating case is more than non-rotating case. So I hope you have understood about how the critical speed is calculated for for the rotor with consideration of mass moment of inertia of disk. Since we consider the mass moment of inertia, we need to calculate two bending moment at a station. One is left hand side of that station, another is the right hand side of station. And because of consideration of bending moment of inertia, we can calculate now non-rotating case and rotating case of critical speeds. So I hope you enjoy this. Thank you for watching.